Right. Now we understood fairly about iron carbon phase diagram, right? We understood there are steels, okay, there are cast iron, and there are different phases among all these types of materials or compositions. Now let us try to see how the microstructure varies from place to place within the diagram. Okay, essentially we bother more about steels. Okay, if we see the steels, if we have carbon percentage less than 2%, we call them steels. Essentially we divided them into two varieties. One is hypoelectroid, second one is hyperelectroid steels. So we have here electroid point, and this is electroid composition. Exactly electroid composition, what happens if you have your liquid and start cooling down, so there will be a point, that is electroid point, where all your austenite, okay, this is solid, okay, this is not liquid. So for eutectic you have liquid, right? Eutectoid transformation is from austenite to ferrite and cementite, right? So in eutectoid you have austenite, right? So looks like this, and once it starts decomposing, you will have ferrite and cementite in alternate lamellars. Okay, you see that lines. Okay, dark line being your cementite and brightest is the ferrite. Okay, so what happens if you have an alloy on the left hand side, any alloy on the left hand side? Assume you have this particular alloy. Okay, you have your austenite again similar to this, your austenite here. And once you start cooling down, there will be a point where you will come to a point where you start first having the ferrite coming out of the solid. Okay, you have, from austenite ferrite starts forming. Okay, because in this particular region what and all you have? Ferrite plus austenite. Okay, so that means in this particular region all that you have to have extra is, you already have austenite, right? You have to have ferrite. So your ferrite starts liberating, okay, until you reach here. Okay, once you reach here, okay, now whatever composition you have, okay, is nothing but, I am talking about the composition of you. Until here you have ferrite plus austenite, right? So your ferrite composition is by going with the lever rule, or by going with the tie line, put a horizontal line here. So you have ferrite, that composition is this, and your cementite, the other one is your austenite, and the austenite composition is this much, right? So in other words, the remaining austenite at this point is having a composition of eutectic composition of austenite, right? So once this, from this point onwards, okay, all this austenite will be decomposed into perlite. Okay, so essentially you have two things in the final product. Okay, if you come here, ferrite and then perlite. Okay, so this ferrite is initially coming out, right? What is the first thing that comes out of hypoelectroid steels? That is ferrite. Okay, we name it as proeutectoid ferrite. Okay, proeutectoid phase. That means until you get a eutectoid composition, what is the phase that you got? Okay, that is ferrite. Okay, initially you got ferrite, that is here. After, once you reach to a point where your remaining austenite is having a composition of perlite, then you will start having perlite liberating. Okay, so that is why you have a combination of ferrite and perlite. Similarly, on the right hand side, you have for the first, once you, if you are here, you again have the same thing like here and here, same austenite. Once it, starts cooling down, once you reach to this point, from this point to any time when you come down, all that you have to have is, okay, your austenite plus cementite. Okay, so what happens? First thing that comes out is cementite here, right? Because you already have austenite, so your cementite starts liberating. Okay, at the grain boundaries. Okay, you see all this grain boundary is having a dark phase, that is cementite. So once you reach until this point, the remaining, okay, austenite, okay, within this we will be having a composition of, at this point, this composition, that is eutectic composition. So once you reach to eutectic composition of this austenite, all this austenite will now be transformed into perlite. Okay, that is what you see here. So in this case, what is the pro-eutectoid phase? It is cementite. Okay, you have cementite and then perlite. Okay, the pro-eutectoid phase for the hypereutectoid steels are is nothing but your cementite, whereas the pro-eutectoid phase for the hypoeutectoid steels, it is ferrite. Okay, you have ferrite first coming out and perlite here. In this case, you have cementite coming first and then forming perlite. Okay, right. Now you know already this perlite structure looks like this. Okay, lamellar mixture of ferrite and cementite. Yeah, we already discussed this hypoeutectoid steels. So what happens if you have less than 0.8%, you have hypoeutectoid, that this line we already discussed. So in low carbon ferrite nucleates and grows, leaving the remaining austenite richer in carbon. Then that carbon will be transformed, that austenite further gets transformed into perlite eventually. Okay, so this is the alloy we are talking about. Okay, hypoeutectoid steel. Okay, similarly, of course, you have primary or pro-eutectoid ferrite in this particular hypoeutectoid steels. Okay, that comes out first, followed by eutectoid reaction. Okay, regions of perlite. Okay, next, hypereutectoid steels on the right hand side, what we have is nothing but in Z to Z dash line, you have a hypereutectoid composition where you have the mixture of cementite and pro-eutectoid or primary cementite. Okay, and then perlite. Okay, right. So I think you have understood about hypo and hypereutectoid steels. Okay, now you see the microstructure for hypereutectoid steels. You see the grain boundaries where you have the primary or pro-eutectoid cementite. First, this is the one first forms from the austenite. Okay, once the remaining austenite have attained the composition of eutectoid composition, then eutectoid reaction happens and perlite forms. Okay, that is second. Okay, the primary phase is this one, that is just cementite, and the secondary formation of phase takes place, that is perlite. Okay, yeah. Just for comparison, ferrite is the soft, ductile and magnetic, austenite soft, moderate strength and non-magnetic. Okay, but cementite is hard and brittle because it is a compound, it is a carbide after all, right? Right. So yeah, the very important thing is all these formations are true if we follow slow cooling. Okay, all these formations are true if we follow the slow cooling rate. Okay, there won't be martensite or bainite or anything like that. Okay, all the previous diagrams are true if you follow very slow cooling. Okay, so in this case the equilibrium phase diagram is no longer valid for engineering analysis because in engineering practice mostly we follow rapid cooling or cooling rates far from the equilibrium cooling rates. Okay, right. So this is the, if you have a very simple phase diagram in the simplest of its rendering, it's having some interactive tools. For example, this is austenite. If I click that, you get the austenite definition, and if you want to see the austenite micrograph, looks like this. So let us go back. So now this is the phase where you have austenite plus liquid, and of course this is just a liquid. So if I come here, it is liquid plus cementite on the right hand side. So this is of course the eutectic point, and below that you have gamma, that is austenite plus cementite, and if you come here you have left hand side, that is ferrite, and right hand side it is austenite. Okay, and if you come here you have ferrite and perlite. Okay, it is hypoeutectoid steel. If you come to the right hand side, it is hyperelectric steels. You have perlite plus cementite. You want to see the microstructure of ferrite, for example, hyperelectric steels. You can see you see the lamellar structure as well as the ferrite. Okay. Similarly, if you want to see the microstructure of hyperelectroid, you can see at the grain boundaries you have cementite and the perlite within the grains. Okay. Right. So yeah. So I think this is useful for you to just understand different phases. It's the same thing that we discussed earlier. Yeah. Now let us move to the next slide. So this is where of course we have discussed three invariant reactions which are more important in iron carbon diagram, that is eutectic, eutectoid and peritectic. Okay, those happen at this iron carbon at carbon percentage and at this temperature, which you may have to remember. Okay, and in eutectic, liquid is transforming to two solids. Eutectoid, one solid transforming to two different solids. So peritectic, liquid plus solid being transformed to one single solid. Okay. These are the uses of phase diagrams. Of course, we can know what are the different phases that are existing, and of course we can also indicate the solid solubility of any phase. Okay, what is the maximum solubility? For example, austenite, what is the maximum solubility of carbon? We know 2% from the diagram. For ferrite, we know maximum solubility 0.025 from the diagram again. So all these things you can easily find from the diagram, and also to indicate the temperatures at which any alloy starts to solidify. Okay, you have at what temperatures these phases exist, all this information you can have. So to indicate the temperature at which different phases start to melt. Okay, not just solidification, melting temperature also you would know. And the final thing is, what is the amount of each phase in two phase mixture can be obtained, that is by using Lever rule. Okay, all these are the uses of phase diagrams you must be knowing. Okay, so with that, the phase diagrams, iron carbon phase diagram discussion will be over. So in the next module, I will try to discuss about the transformation, time temperature transformation diagram. Okay, and also about the continuous cooling curves. Okay, thank you.